Pluto is a distant and more unpretentious planet that was once a piece of our close-by planetary structure. Anyway, advancing disturbing statements by driving astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They propose that this far-off world is on a potential impact course with Neptune. Yet how could this be able to genuinely work? Likewise, what might be the results of such an immense event? Are we seeing a confounding, immense eccentricity, or is there something else to this coming interminable accident? Join us as we take a gander at the probable results of a Pluto-Neptune crash. Pluto, a past planet that was renamed as a dwarf planet, remains a subject of interest in the immense universe, as shown by ongoing guesses by driving topic specialists. Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential perilous incident between these two planets, which could infer a colossal risk to Earth. Anyway, how is such an event indeed even possible? Pluto's excursion around the Sun is unlike that of any other planet in our nearby planet group. It requires a staggering 248 years to complete a solitary circle. Since its discovery in 1930, it hasn't even finished one full orbit. In any case, the interest doesn't stop there. Pluto's orbit is marked by its particularly bended shape, meandering extensively from the nearly round orbits of the significant planets. What makes Pluto's orbit significantly more surprising is its inclination, which is 17 degrees to the ecliptic plane. The manner in which Pluto follows its way is altogether more flighty compared to other planets. This inclination and inconsistency add layers of complexity to its orbital arrangement. Possibly one of the most interesting bits of Pluto's orbit is its union with Neptune's. For around 20 years in each orbit, Pluto actually moves nearer to the Sun than Neptune, contradicting what we could anticipate from their positions in the planetary system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of various planets. The appraisal of Pluto's orbit started not long after its discovery. Initially, space specialists attempted to sort out its unique way. Unlike other planets whose orbits lie somewhat near the ecliptic plane, Pluto's orbit stands out with its steep inclination and whimsical shape. The mystery grew with the acknowledgement that Pluto's orbit truly does, without a doubt, cross Neptune's. The stability of Pluto's orbit, not enduring these complexities, is confirmation of the intricacies of celestial mechanics. The three-body problem in space involves deciding how three objects in space, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like attempting to predict where they will go based on where they started and how they pull on each other. For Pluto's circumstance, this issue shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a convoluted way. The terms non-synchronous libration, orbital precession, and VZK wobbling are critical to this conundrum, as made sense of by astrophysicists. What keeps all planets in their orbits is non-synchronous libration. Concerning Pluto and Neptune, this term basically implies that when Pluto crosses Neptune's orbit, it is situated about 90 degrees away from Neptune. This spatial division is vital in holding their orbits back from meeting. Orbital precession, on the other hand, alludes to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated far above their orbital plane, adding an additional layer of security from potential crashes. One more key factor in this situation is the VZK wobbling, named after three researchers, Zell, Kai, and Kaku, who studied how objects move in space. It involves how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling influences how they move. For Pluto's case, the VZK wobbling assists us in figuring out why its orbit, close to the Sun, is so unpredictable. In spite of Pluto's orbit appearing to be wild, this wobbling helps keep it moving smoothly over extended periods. The VZK wobbling shows that, notwithstanding things in space appearing to be wild and abnormal, examples and rules keep things under control. These forces help keep Pluto's orbit stable, ensuring that it doesn't crash into Neptune or drift off course. This three-body problem is critical to understanding how these orbits change because of the manner in which space objects pull on each other. Concentrating on this helps us learn more about Pluto, our nearby planet group, and indeed, even far-off systems and their stars. Numerical simulations in the late 1980s revealed that, notwithstanding the balancing out properties, Pluto's orbit is, in reality, sporadic, with minor deviations in initial conditions leading to massive differences over many years. However, these characteristics of Pluto's orbit have been found to maintain stability over incredibly long timescales. Actually, looking at the perturbations from later computerized evaluations has helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's orbit around the Sun. Neptune has an extraordinary relationship with Pluto, where for each 2 orbits Pluto makes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only one at work. Jupiter's gravity also plays a huge role in stabilizing Pluto's orbit. Saturn too contributes. These studies show that Jupiter's enormous gravity is strong enough to ensure Pluto stays on a steady path for a really long time, potentially even for a long, significant stretch of time. So, maybe Neptune, Jupiter, and Saturn are coordinating to ensure Pluto continues to move safely through space without running into trouble. These quirks are significant for keeping everything in place. Without these components, the nearby planetary system, as we probably know it, would be a much harsher spot. Bodies like Pluto could collide with others or be shot out from their stable orbits, setting off a chain reaction with other celestial bodies. For Pluto, especially with concerns about it potentially crashing into Neptune later on, understanding its orbit is fundamental. This gives a clearer image of the powerful idea of the close-by planetary group. The instance of Pluto shows how even the most apparently temperamental circles can reach a condition of balance through the complex interaction of gravitational forces and orbital mechanics. It additionally highlights the significance of consistent observation and analysis of these quirks to better understand our position in the universe. Examining the depth of space frequently forces us to confront the uncommon nature of celestial bodies. Additionally, Pluto's orbit is an ideal example of this inconsistency. The idea of orbital disorder, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can drastically modify its long-term orbit. Using computerized simulations has been tremendously helpful for scientists in figuring out how Pluto moves in space. These simulations use complex mathematics to demonstrate how Pluto and other space objects, like Neptune, pull on each other. By tweaking small details in the simulations, space researchers can see how even minute changes can make a huge difference in where Pluto ends up. In the late 1980s, these simulations showed something intriguing about Pluto's orbit. Despite having features like non-synchronous libration and orbital precession to keep it stable, its orbit can still be inconsistent and surprising. If you start with just a small difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after only a couple of years. Yet, despite this tumult, Pluto's orbit remains stable over vast timescales, like billions of years. This means that Pluto's journey around the Sun has a sort of order to it, even though it appears chaotic at first. Predicting celestial movements, especially when they involve irregular orbits like Pluto's, goes beyond a gigantic challenge. The inherent irregularity of these systems means that long-term predictions are often filled with uncertainties. While mathematical models provide amazing tools for understanding and predicting the future movements of celestial bodies, they also highlight the limits of our predictive abilities. These models heavily depend on the accuracy of initial conditions, and any small error or distortion can lead to vastly different outcomes, making exact conjectures a daunting task. Beyond the tumultuous nature of planetary orbits, Pluto reminds us of the ever-changing and dynamic nature of the universe. While we've made tremendous progress in understanding space, Pluto's case serves as a reminder of how much our knowledge of the universe still remains limited. Grasping the gravitational effects of the giant planets on Pluto's orbit gives valuable insights into the broader dynamics of the nearby planetary group. It shows how the presence and position of each planet can significantly influence the stability and direction of other bodies within the system. So why are leading astrophysicists recently raising concerns about a potential collision between Pluto and Neptune? Despite all these complex forces working to prevent such an event from happening, Neil deGrasse Tyson, a prominent astrophysicist and a key figure in advancing cosmology, offers a unique perspective on the mysteries of our planetary system, especially the intriguing case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, offers insightful analysis on the evolving nature of celestial mechanics and the public's interest in the neglected corners of space. Tyson's position on Pluto's renaming is based on the continuously developing understanding of our planetary system. He sees the renaming not as a diminishment but as a significant adjustment to our growing comprehension of the different bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of constant learning and change. He sees the intricacies of orbits like Pluto's as a sign of how much there is still to discover in space. The fascination with these questions keeps the exploration of space so intriguing. However, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the fate of Pluto, once a planet, stem from his understanding of the erratic nature of these orbits. Tyson acknowledges that while Pluto's orbit has remained stable thus far, small shifts over time could lead to catastrophic events. The path of Pluto, especially its intersection with Neptune's orbit, is a complex cosmic dance that may not always remain stable. In Tyson's view, even small disturbances in Pluto's orbit could have significant lasting effects. If these movements accumulate over thousands or millions of years, they could eventually result in a more unpredictable outcome, possibly even a collision with Neptune. However, these events wouldn't happen anytime soon. Instead, they might unfold over long periods, far beyond human lifetimes. All things considered, Tyson's precautionary stance underscores the importance of continued observation and understanding of Pluto's orbital dynamics. Tyson isn't alone in his views. Michio Kaku, a theoretical physicist, also discusses the potential chaos that could unfold from planetary interactions within the solar system. While Kaku shares Tyson's enthusiasm for exploring the wonders of the universe, he also recognizes the inherent instability of planetary orbits and the unpredictable effects that could arise over time. Both Kaku and Tyson emphasize the importance of ongoing analysis into the forces that govern planetary movement and the future of our solar system. Ultimately, the case of Pluto serves as a reminder that our understanding of the universe is ever-evolving, and new discoveries often lead to more questions than answers. As astronomy continues to develop, the possibility of an event like a Pluto-Neptune collision reminds us that space is full of surprises, and the seemingly stable orbits of planets could be subject to dramatic changes in the future. These reflections on Pluto remind us of the importance of keeping our eyes trained on the stars and our minds open to the mysteries that still lie ahead.